Hello, good afternoon everyone. Welcome to our tutorial on semantic specialization of distributional representation models. So maybe you see like a deliberate change in the title, so we moved from vectors to models, and part of the reason is basically that in between the tutorial submission and tutorial presentation there has been quite a lot of interesting work also on specializing or inducing or injecting knowledge into these contextualized word representations and like encoders like BERT. So we wanted to also cover that spectrum of models and also draw some connections with previous work which was focused more on static word embeddings. So we have plenty of material to cover, so maybe we won't actually dig deep into all of the topics that we have on our slides. The slides will be available online and quite soonish, so you'll be informed about that. So quickly, the tutorial will first introduce the need to actually specialize distribution representation models, both static and non-static, contextualized ones. We'll briefly cover some of the main lexical relations, external repositories, and why we kind of need both. So this will be like an easy part. Then we'll switch to specialization for the symmetric relation of semantic similarity. And we'll actually do like a typology of different models that do this sort of specialization there. Then we're moving towards other relations, including asymmetric relations like lexical entailment and meronymy. And we also show some other work that actually did specializations for like different relations like Babelnet style relations or morphological relations, etc. And then we'll show how to do specialization via transfer or joint multilingual modeling in resource poor languages, so we can say it's cross-lingual transfer. And finally, like a dedicated part, will focus on specialization and knowledge injection into contextualized representation models. So that will be the last part given by Eduardo, and after the tutorial you will have some time for questions, etc. So basically the goals of the tutorial are providing the overview of these methods that kind of combine distributional training, distributional, call it co-occurrence knowledge, with discrete external knowledge that is available in all these external repositories. So we're here mostly focusing maybe on linguistic, lexico-semantic resources, because you already see this might actually have tight connections to like knowledge-based embeddings and injecting knowledge from more like general KBs like, I don't know, Freebase, DBpedia into the models, but we're focusing more on the linguistic, lexico-semantic aspects. And we'll try to show that both for static and contextualized word embeddings, symmetric and asymmetric relations, and also see some of the challenges. So one of the things is how to deal with incomplete information, because even like the largest repos that we have like WordNet are usually incomplete, do not contain information for all the words and word pairs and like groups of words, etc. An interesting part is also how to deal with this incompleteness and scarcity of resources in other languages. And finally, like, why do we need specialization in the first place? So what sorts of downstream applications are actually supported by different specializations that we make? So if we specialize for similarity versus relatedness, do we actually cover a different spectrum of downstream applications? And we'll also list some challenges and open problems, and we'll actually even do like quick detours to other related fields of work, which also really touch upon this basic idea of semantic specialization. So well motivated from like an example that I often like to give, and it's basically why we need to specialize our distributional vectors, for example, to differentiate between true semantic similarity and call it broader conceptual association or relatedness. So you often want to do the distinction, for example, for language understanding applications like dialogue. So if you want to have like a data-driven language understanding system for dialogue that performs your dialogue state tracking, you kind of don't want to mix up cheap and expensive or British and Spanish, etc. Although from another relatedness perspective, these are considered related. So, for example, if you have this like dialogue here, if everything goes according to plan, your word vectors give you the generalization capabilities. Actually, your language understanding system will understand everything that the user said. But what happens in the reality, if you don't really capture true semantic similarity, is that you will actually get exactly the opposite. So you already see that this will be a totally disastrous dialogue from the user perspective, because she wouldn't get what she actually wanted. So like, you don't want an expensive restaurant in West Cambridge, for example, if you want like a cheap pub in South Oxford or things like that. So that's one reason why we maybe want to steer our distribution representations to actually capture true semantic similarity. Another application that we also cover is text simplification, where the task is quite simple. You just want to replace lexical items in the input text with simpler words, and at the same time you want to preserve the meaning of your input sentence. So if you do not distinguish between true semantic similarity and relatedness, you might actually get really weird sentences. So if you replace pilot with airplane, which are like two related lexical items, and if you replace victory with the antonym, which is defeat, you kind of completely lose the meaning of the sentence. So that's another reason why we need it. So basically the whole work actually started. So this is all like historical evidence, because we wanted to really distinguish between similarity and relatedness, and to have this profound effect on how our distributional vector spaces are arranged, to actually emphasize, call it synonymy, and de-emphasize antonymy, to actually capture this true semantic similarity. And that way you can actually really capture like the synonymy relationship, for example. So your nearest neighbors of east won't be west, north, and south anymore, because that might completely destroy your language understanding system. But really, all the items that are still related to the to the location of east or towards east, like eastward, eastern, easterly, etc. So that started the whole thing, but now a curious fact is that specialization as the idea and specialized vectors actually found even some unexpected applications. So they are now used in biomedical NLP, because you can kind of inject the knowledge from, biomedical thesauri or synonymy relations in your particular domain. And there have been some analysis how it actually reflects the human lexicon in the cognitive science psychology research. We also use it for like debiasing work, which is quite popular in NLP these days, and it's been used, for like fact-checking, detection of abusive language. And when people started working on specialization, they really didn't have all these applications in mind. From the lexical semantics perspective, I think the motivational question is quite simple. It's basically, if we have like a trained distributional model, think of word-to-vec models, can we really distinguish between different well-defined lexicosemantic relations just given the distributional vector space? And the answer is no, we can't really do it in an unsupervised way. So if we just feed those vectors as features into our downstream systems, you get all these different relations conflated, like synonymy, antonymy, meronymy, cohyponymy, and as we said, we don't want car and driver maybe to be close to each other in a vector space if we are doing text simplification, for example. Okay, so basically the main idea is to combine like these two sources of information. So the first one is learning from distributional signals. So I think the main idea behind distributional semantics is learning from the data, or trying this Furtian or Wittgensteinian hypothesis that we can just define meaning as use, and the word has meaning only when it co-occurs with other words. And basically all the main paradigms that we use, like call it pre-training or call it word embeddings, they're still relying exactly on this assumption, just learning from raw text. So word2vec actually learned from these word co-occurrence windows or dependency relations in local neighborhoods, more or less, which is actually a successor of Benjo et al.'s language model, more like call it like a lightweight version without like a full-fledged language model that needs to be trained. And then we went back again to training language models, which still kind of rely on preceding or succeeding history of the current word, which is more or less local distributional information. And so I took this slide from Thomas Wolff, which also to again emphasize that although we kind of switched from more like static vectors to these contextualized models, they still rely on local distribution co-occurrence. So it's basically the limits of the distribution world are still there. And we kind of have to resort to other sources of information to enrich, to complement these representations and learn richer features that can actually help us solve like a wide array of tasks. So that's pretty much what I just said. So you can actually have these enrichments across different axes. So for example, like you can add the knowledge from semantic lexicons like synonymy antonymy relationships, or you can try to maybe for languages with rich morphology learn better features for morphological inflections of certain words, or you can actually also ground your meaning cross-lingually or multimodally, etc. So the idea behind specialization is really to enrich the vector spaces, make them more informed by combining it with other source information, and specialize them towards the particular direction. Okay, think of it as true similarity versus relatedness as the easiest case. Okay, so then another question appears is like, okay, so if we have really good lexicosemantic resources, like, do we then need distribution knowledge at all? But there's also a problem with lexicosemantic resources like WordNet, because even for resource-rich languages, they have limited coverage. So, like, the stats here is that the top 200 in the top 200,000 words of fast text English vectors, only 15% of the word types are covered in the whole English WordNet. And you can imagine what happens even when you move to other languages which are not even resource poor. Like we do have open multilingual WordNet, for example, but it's not as complete as English WordNet. And then also, like, how do you define similarity of meanings across the WordNet knowledge base or graph? This also seems to work worse than some of our distributional methods. So it's basically, this kind of calls for merging the two different paradigms in this work. Okay, so before we actually start with the proper specialization, so we'll mention a few related research threads that are also really closely related to the core specialization idea. So the first one is learning from context. So when people started inducing all these word embeddings like skipgram and cbow and fast text, there has been some work that actually realized, okay, by manipulating the context you feed into the model, for example, for the skipgram training, you can actually steer your embedding spaces towards similarity versus relatedness. So your resulting word vectors will actually boost more like true similarity language understanding task, where there's some tasks where you need like more broader topical relatedness, like document classification, etc. So the ordinary context type is just like local context windows for skipgram, but you can also enrich it with positions. So if you have neighborhoods, you can say, okay, this word is occurring as the most left neighbor, this one is the second left neighbor, etc. Or you can use dependency arcs that connect words with their neighboring words, and etc. And you can also use additional context from the outside, like cross-lingual perceptual context. And basically, by manipulating this context, you can actually get different vector spaces with different neighborhoods. So, for example, you see here the table from Levy and Goldberg's work, ACL 2014, already seems like ages ago, where like instead of using bag of words contexts, where you get, more like truly similar words as nearest neighbors, dependency contexts also kind of reflect the grammaticality or similarity in grammaticality, because you can see that all the nearest neighbors and of dancing also are kind of semantically related and end up with the same suffix. And Melamud et al. Also realized, so when they evaluated on similarity benchmarks instead of relatedness benchmarks, that like different contexts have peak scores on different benchmarks. So that was, but this is all kind of just manipulating the context in an unsupervised way. And then you can like even impose more richer context, so context to vec paper, instead of doing like the SIBO thing where you just sum up all the local neighboring words. They actually had like full-fledged sentential context implemented as bidirectional LSTMs, and this emphasized functional similarity through similarity even more. So we saw some really nice results on, for example, verb similarity benchmarks that we're going to talk more about later on. And people have tried different things. So there's been like a version of SIBO or skipgram that also applies attention. So you kind of weigh different neighbors differently to emphasize that some neighbors are more important for learning that particular word. And there's also the idea of substitute vectors, where you're trying to, it's kind of now related to what BERT does in a sense, where you kind of say masking one word, and then your contexts are words that can fill that masked slot. And that also helped in certain tasks like lexical substitution, and I think that there were other applications, and there has been some work on trying to sample just contexts that are useful for a particular word class. So you want to build like noun-specific versus verb-specific word vectors, etc. And so the bottom line is it's still limited, because it's still kind of just manipulating your distributional signal in one way or another, and we can't actually get extra information on top of our distributional training. So as I already mentioned, we can now talk also about cross-lingual grounding, multimodal grounding, which is related because it's also sort of adding external information into monolingual distributional vectors, but we simply don't have time for that, so I'm just skipping that. Another related thread is also unsupervised post-processing of word vectors, which could be seen as unsupervised specialization in a sense, where the idea is again to improve our representations before injecting anything. And there has been some work on that, even like very recent work. So one idea from Mu et al., I think the paper's name is All But the Top, is basically to kind of do the PCA on your mean-centered word vectors after you train it, and you just remove 2 or 3 dominant PCA components, and it seems to really help with similarity, and you get some small similarity boosts on similarity benchmarks. And that result is slightly counterintuitive, because these dimensions that you remove kind of contain a lot of most important information about the vector space, but it seems to, like they claim, it increases isotropy of the space, and that can then help similarity. I don't fully capture why, but that's basically more like an empirical result. And Artech et al. Also showed that you can do like a small linear transformation of the input distributional space to get it more towards relatedness versus similarity. And I think the idea is kind of to emphasize different orders of similarity and then learn this transformation, which is like a single parameter model, and then controlling this alpha, you can steer it towards similarity versus relatedness. So that's a pretty simple but nice paper that's Connell last year, I think. But again, without any external knowledge, even if you do this unsupervised post-processing, the gains that you get on the tasks are really small, and they have been tested mostly on intrinsic benchmarks. So, okay, that was a detour. So, in a very short recap now. Okay, the key idea is to really get the information from our lexicosemantic databases into our distributionally trained word vectors, and do it for particular relations that have different properties. So think of it like symmetric versus asymmetric, and also can we transfer that knowledge into other languages, and what to do when our distribution information is not good enough, and etc. etc. Okay, so now comes the boring part that I'll just slowly go through on like lexical relations and lexical resources. So it's basically the main message is, okay, so like we as the community, we kind of like doing our models in an unsupervised way with like the minimum amount of information in supervision coming from the outside. But if we already have some of the resources, like we shouldn't be shy and not use them, because sometimes it's just for pragmatic reasons, it's better to use the information we already have. So if our goal is to get to like production level NLP, for example, or from the in academic terms, optimize downstream performance, why not make use of the available lexical resources? And why not try to generate more for resource poor languages? So there's like plenty, like Babelnet, paraphrased, ConceptNet, WordNet, etc. You probably all know it. I'm not going to talk about WordNet, really. This is just for completeness. And so, okay, I'm going to talk a bit. So it's just to illustrate that, okay, we like when you think specialization, maybe think specialization through semantic similarity or synonymy versus specialization for hypernymy, or you can even specialize your vector space to capture meronymy really good, or like any other function or relation, etc. Okay, so something. So my slides do not move anymore. Okay, this is just some general statistics from WordNet showing that we do have a lot of knowledge coded. I mean, it's been years and years of work of expert linguists to do it. Then there are other resources that were created in semi-automatic way, like Paraphrase Database, for example, that was created to this bilingual pivoting between parallel corpora. And there's also FrameNet, so you can even like use the FrameNet knowledge to do your specialization. There is like VerbNet, so you can even specialize to emphasize your the similarity, VerbNet style syntactic semantic similarity between verbs in your vector space, etc. And so yeah, some statistics about PPDB. Probably you know that actually it comes in different sizes, and larger PPDBs are often noisier because they impose less, like more lenient thresholds on the data extraction protocol. And so that's also an open question. Like, do we need less cleaner knowledge, or maybe we want more abundant repos that have also some noise and how to get rid of the noise? But I'm not going to talk about that. So the thing that we should know about PPDB is also that it's now available in, I think, maybe I have the stats now, 17 languages or something, that you have like lexical paraphrases. That it's also annotated partly for antonymy and lexical entailment. It also has lexical and phrasal paraphrases, and it's a quite useful resource for these types of things like specialization. Then there's Babelnet, which is like an ever-growing, continually growing resource that actually is trying to be as multilingual as possible. So it currently covers 284 languages with like more than 6 million concepts. And this is like really one of the resources which boosted the whole work on specialization, which also has like these multilingual synsets and taxonomic relations. It actually, yeah, it's one of the most used resources in this specialization work. So this is an example of from Babelnet, where you have like these, as I said, multilingual synsets, translations. You even have some visual information. So if you want to do like multimodal grounding, that could be also useful. You also have definitions. So there's a line of work that also tries to use the knowledge from the concept definitions as sort of guidance for purely distributional models. We're not going to talk about that as well. I just have 2 slides later on. And yeah, so these are like the general statistics, and again, the main message is we do have this resource, so can we use it complementary to the distributional training? So, for example, yeah, from a very broad perspective is, for example, can we merge Babelnet and BERT and get something useful out of it? Because yeah, they both seem quite powerful in its own right. Just from like these 2 different perspectives of continuous versus discrete representations. There's also ConceptNet, which also includes like a lot of common sense lexical relations. And it also builds on top of Wiktionary, and it includes open multilingual WordNet. So again, something that's quite useful. Okay, so that kind of concludes this part of introduction motivation. And now we move towards the actual specialization work. So we'll now give a brief overview of the current research thread that specializes. We're still talking about static word vectors. So think of it like Word2Vec style for semantic similarity. Okay, so we'll cover actually 4 different types of models called joint specialization models, retrofitting or post-processing models, and 2 lines of work which are actually similar to retrofitting called post-specialization and direct or explicit specialization. So you'll actually learn the distinction between the 4 in like 30 minutes or so. So first defining true word similarity, like what is word similarity? So it's not really like a proper linguist, well-defined relation. So it's more like maybe a layman's view would be like something like graded synonymy, but it also means that words that stand in other WordNet style lexical relations like hypernymy or like one-pad, two-pad hypernymy also can have really strong similarity scores, and that's what like Felix Hill and colleagues actually showed in the Simlex paper that, yeah, for example, the strongest scores on true word similarity are for true synonyms and one-pad, one-hop hypernyms from the word hierarchy, which kind of makes sense because you often can also replace hypernyms in similar contexts. And then they also showed that like they use USF norms as sort of like association/relatedness benchmark, and show that some other relations actually have better scores than synonyms when you're trying to capture relatedness. So, for example, antonyms have a higher association score than synonyms in the USF database. So, in order to really evaluate what our word vectors capture, we kind of need all these evaluation resources. So, people have spent a lot of time building intrinsic evaluation resources for different types of relationships. So first, we didn't even really like distinguish between similarity and relatedness. So like these historic data sets, like even some more recent ones, kind of conflate similarity and relatedness. So you like even really well-known data sets like MEN do that. And there's also a data set that captures graded lexical entailment called Hyperlex. Then you have data sets on word analogy, and there are also data sets that capture semantic similarity, which are decoupled from the relatedness/association type of thing. So you have the list here. So some of them were translated to other languages. So there's like multilingual Simlex 999. Now Hyperlex has also been translated to 4 or 5 more languages, and there are also other multilingual cross-lingual data sets from the Semeval task from slightly more than 2 years ago. Okay, so this is, again, I said it too many times, a slide that shows that similarity and relatedness actually anti-correlate. So if you take a data set that captures similarity, and if you take a data set that captures relatedness, and if you start specializing your model to capture similarity, your similarity scores actually go up while your relatedness scores go down. And so that's like, so we really saw that when specializing with one of the models that you'll actually see quite soon. And another slide that also shows that if you annotate the same word pairs for similarity, which is captured in Simlex 999, versus lexical entailment, which is captured in Hyperlex, you actually get different scores with different models. So sometimes they even like, there's no even correlation at all on exactly the same word pairs, just annotated for different relationships. So if you ask people to what extent is concept X equal to Y, instead of to what extent is concept X a type of Y, it's a different relationship between lexical items. Okay, so we'll show some results also on downstream applications. I already mentioned like the task of dialogue state tracking, which could be seen as language understanding for dialogue. I'm not going into specifics of how these models work, but what you have to kind of understand is that many of the recent work on dialogue is based on distributional models. It's like purely data-driven, trying to learn based on word vectors or like BERT-style models and different encodings of text, which basically means that we need to do this distinction between similarity and relatedness. So this graph here is kind of just an overview graph of a completely fully data-driven neural pipeline for dialogue state tracking. You don't have to understand it. It's basically, again, just to mention that, yeah, distribution representations are kind of the lifeblood of these models. So why not inject external information if we have it explicitly into these features and just get better features that for the application. And the same thing goes for lexical text simplification. Already mentioned this or a similar example. And there are also tools that are trying to do simplification without manually handcrafted corpora, just relying on basically on word embeddings. So there's this like light lexical simplification tool that does exactly that. So can we get rid of manually simplified corpora and learn better simplification models? So that's another application that we're going to cover. Okay, so now we are moving towards modeling. So first we're going to talk about two different groups of models. The first group is called joint. Let's call it heavyweight approaches. We'll see why they're heavyweight. And the second group are these post-processing approaches. So the idea behind joint specialization models is basically to combine your distributional training with another objective that injects external lexical knowledge immediately into the training. So you actually kind of have this joint training of both objectives, distributional and the resource-based one. And a good thing about it is basically that your training, it kind of affects all words in your vocabulary, because through distributional training, if you affect something that's, if you have a word pair from your resource, it will get affected by the resource-based objective, but you also have these words in your distributional objective, so it kind of gets propagated. And the problem is that if you want to inject that into a joint model, like if you want to work with another resource, if you want to work with another model, you always have to retrain from scratch. And if you train a large corpora, like, I don't know, a couple of billions of word tokens, even more, it basically means constant retraining whenever you change something. So that's why people actually design post-processing models, where the idea is to kind of use it as a black box. You just have your pre-trained vector space, you put it into that box, and you get your specialized vector space out. So that's the main idea. The problem is that the first retrofitting post-processing models can affect only vectors of words that are seen in external resources. Also empirically, people found out that although there is no like theoretical proof for that usually you get much better performance with these post-processing models, because with joint models maybe you need to do again like extensive hyperparameter fine-tuning, which is again really expensive because you have large corpora, etc. So like the joint work has been replaced by post-processing methods recently. Okay, so a tiny bit about constraints. So we'll mostly talk about linguistic constraints, which are given in a really simple format, which is just like a pairwise format. Which basically means, okay, these two words stand in the relation of synonymy, which is useful for true similarity, or antonymy, which is not useful for true similarity. You can, like on a more general note, you can also think of triplets, where you have word 1, word 2, and the relation between them. So this simple format actually also allows us to kind of extract knowledge from like different knowledge bases and just combine them into a single model. And if you have it in other languages, it's really simple to like do mixing and matching. And this is pretty much the format we're going to use throughout the tutorial. Okay, so now I'm giving a brief overview of joint specialization models, even starting from pre-embedding time. So one of the methods that I kind of like is this work from Yi et al. EMLP 12, where they wanted to really clearly distinguish between synonymy and antonymy, and what they did was in the word co-occurrence matrix that is needed before applying your LSA model, that I actually negated the entries of antonyms. And it was shown that way they can learn vectors that really do the distinction later on. And I think the model worked really good for the lexical contrast capturing, etc. So the idea of specialization kind of existed even in pre-embedding times. Okay, so now we're moving towards the main idea behind joint specialization models. So this is one of the seminal papers, ACL 2014 from Yu and Dredze. And the idea is actually, as I mentioned, quite simple. So as you pretty much know how SIBO and skipgram works. The idea is to combine the distributional objective of SIBO or skipgram with the knowledge resource objective, which is given in exactly the same format as your SIBO or skipgram objective. You're just taking word pairs from your linguistic constraints. And then based on the type of relation that you want to capture, synonymy versus antonymy, or versus something else, you can actually steer your vector space towards different properties and specialize it. So exactly the same idea, more or less, was tried out by Keela et al. At the MLP 2015, where they were like the first ones that really like emphasized this relationship, or like anti-relationship between relatedness and similarity. They also used like a skipgram with negative sampling objective with pretty much exactly the same knowledge resource objective as the previous model from Redze. And they tried different variants where they use all linguistic constraints in the resource-based objective, or where they just sample one additional context for that. So imagine if you have word X standing in a synonym relation with more than one word, then you will just sample randomly one of the synonyms for that word when you train the model. It's kind of not to overemphasize the contribution of the lexical resource. And they also try to do a sort of retrofitting where you first train your distributional model. Once you're done, you continue training the model, but now using only the resource-based objective. And they evaluated on similarity versus relatedness data sets, and okay, it's here. And basically, they showed if you use, association relationships from USF versus thesauri information from like some synonymy thesaurus or something like that, you can actually get better scores for Simlex with similarity specialization, better scores on MEN, which captures relatedness with association-based specialization. And it also, I think, propagated to some of the downstream tasks they had, like test classification or something. And as you see here, this objective is quite general. So as I said, you can actually plug in any pairwise constraints that capture different relationships here and get your specialization for that relationship. That's like in theory, and it's oversimplifying, but yeah, let's just pretend that it's true. Then there were other ideas. For example, this model from Leo et al., they kind of imposed ordinal constraints along with the distributional objective. And the idea is if you have two words in your constraint set, you want to rank them higher than like similarity of some other of some other word which is also stands in a relation with the first word. So for example, similarity of words that are really direct synonyms should be higher than the similarity of antonyms, and then they had like a list of rules how to actually impose these ordinal constraints on the model, and then they traded as a constraint optimization problem like a skipgram style objective with the resource-based objective based on these ordinal constraints. So that was the idea. This is also another work that I mentioned for completeness, where the idea was this is like a different perspective on learning the distribution model, which is based on CCA, and then there's like a place where you can also inject your prior knowledge during one of the stages of the model. Like, I forgot the specifics, to be honest, how the whole model works. It's like mathematically more complex than skipgram. And yeah, it's an interesting model that didn't really reach the peak scores, if I remember correctly. And then there was another similar model that also, I think the interesting thing about this is basically they tried to kind of increase the set of constraints by doing like, I don't know, second order constraints, saying like friend of a friend is my friend, meaning like synonym of a synonym should be a synonym, or like antonym of a synonym should also be what? I don't know, but you understand the difference. And then they trade like the like a skipgram style model only on these word pairs from constraints. This is like WET model, and they also combine it the same way Keela et al. Did, Redze did, but now with like distributional training. And that's about joint models. And so this is one slide about specialization from definitions. So often you do have dictionaries that kind of have these short definitions of concepts. So one of the ideas was also like to enrich skipgram training with word pairs that actually are extracted from these definitions. And then Tissier et al. Did this paper where they have this terminology like strong pairs, which are, I think, words that appear in each other's definitions, and weak pairs where only one word appears in the definition of the other, but not the other way around. And they kind of they call it positive sampling because they want to emphasize the similarity between those words that appear in strong pairs and weak pairs, etc., etc. But in the essence, it's again like one of the joint specialization models. And another interesting idea from Bosque and Vincent was learning your specialized word embeddings while trying to autoencode dictionary definitions, and then you kind of hope that during the autoencoding part, you will also learn better embeddings that capture similarity in a better way. So, okay, so these were all, as I mentioned, heavyweight models because they need retraining from large text corpora anytime you want to change something that tied to the underlying distributional architecture, and that's why we actually wanted to move to retrofitting and friends. So the idea behind retrofitting is super simple, although it was written like it's a Schrödinger's equation, but it's actually so simple. So the idea is, okay, you have a pairwise constraint, and what you want to do is basically bring those words closer together in a vector space, and you implement it as like minimizing the Euclidean distances. So it's, yeah, it's, oops, where did I go now? So it's this term here. So if you have a constraint, yeah, just try to minimize this. At the same time, you kind of want, because your distribution training was still quite useful, because you have a lot of useful knowledge there, you want to keep them close to their original distributional estimates. And that's pretty much it. That's the whole philosophy of retrofitting and most of the other models. Or if you want like a graph-based reinterpretation, you kind of want to respect two word adjacency matrices, where the first one is the one based on your constraints. So you want like word vectors of words from constraints close to each other while not moving far away from the distributional estimates. And you optimize this cost function, and that's the basics of retrofitting. Then another model appeared, which is counterfitting, where the novelty was basically that they also added the antonym term, where you also want to get rid of the antonyms, because I mentioned this example with language understanding, where you want to distinguish between north and south really explicitly in the vector space. And we can have a debate what to do with the antonyms later on, because that's the question I often get, like what to do with the antonyms. They shouldn't be maybe far apart in the space, but yeah, that's a linguistic debate for later. From the pragmatic perspective, they just wanted to get rid of them for the dialogue task. And their objective is slightly different. It's basically, but it's again just minimizing the distance. I think it was operationalized as a cosine distance here. Between minimizing distance between synonyms, maximizing the distance between antonyms, and the third term is again regularization, which is now slightly different than in the original retrofitting. The idea is to kind of take the neighborhood, a local neighborhood of the word, which means like all the words that are in the radius based on the cosine distance below a certain threshold, and try to minimize the original distributional distances, difference between original distribution distances and now distances of specialized vectors. So that's the vector space preservation term. The problem with that term was actually that it was really costly for large neighborhoods, for example. And then you combine these three terms into a joint objective. So that's the rough idea of counterfitting. Okay. Then another method which is really popular is the paragram method, where again the idea is it's exactly the same. You just want to drag words from your synonymic constraints closer together in the vector space. The only thing is that it's implemented in a different way. So the way you do it here is, you go over like mini batches of constraints. So think of like you have a list of 100 constraints, and you want to push you want to push like the word from the constraint by a margin closer to its constraint paired word than a negative example of that word. And the negative example is taken as the most similar word from the current batch, mini batch, that is not in the constraints with the first word. It's a bit complicated to explain it in simple words, but the actual process is much simpler than that. So yeah, let's just say, okay, I can actually try to do it again when we have an overview, but that's the main idea. And you just proceed in these like mini batch training, and you're doing like this max margin learning framework, and you're attracting synonyms closer together in the paragraph method. So that's the main idea. And so I already mentioned this. The actual trick or tweak is in the way you select your negative examples. So for each word in the pair, you take the most similar one, which is not from the current mini batch, which is not in the constraints with the left or the right word, and then you force it to be you force the positive pair to be by a margin closer than when you pair it with the negative example. And this is exactly the same idea, just illustrated, but I'm not going to spend more time on that. And the paragraph method, again, moved back to the original regularization of retrofitting. It's just like a simple Euclidean distance minimization between the original distributional estimate and your specialized vector, which is also which can be fine-tuned with this additional lambda parameter. But usually we found out in our experiments that just fixing it to like a small value, I think 10 to minus 9 actually works the best, so it doesn't really involve a lot of fine-tuning. Okay, so the Attractor Pell model is then basically like an extension of the paragraph models, which, again, similar to counterfeiting, included this Repel term where you want to get rid of your antonyms. And the idea is analogous to the Attractor. The only thing that you do here is you're trying to push like two antonym words by a margin further apart than the vector of the negative example. And the way you select the negative example is now the least similar word in the current mini batch to the word from your antonymy pair. And so this is like the illustration of what is going on. So yeah, so if you go like constraint by constraint in a mini batch, select your negative examples for each of the words in the antonymy word pairs, and then try to push the positive pairs by a margin further away. And then, as with counterfeiting, you combine again like these three main objectives. So this is illustration of the whole thing: the attract objective, the repel objective, and the regularization objective. So that's the main idea. So basically, you can see that it's quite similar to counterfeiting, and the high-level idea is pretty much exactly the same. It's just the differences in regularization and the way you actually do the updates for the attract and repel terms are quite different, and it actually leads to differences in results with the two methods. So one thing to mention here is that the linguistic constraints are actually like the main driving force behind the specialization method when you do post-processing. So like it's basically junk in, junk out, or non-junk in, non-junk out. So if you want to specialize for true semantic similarity, you can even like put additional constraints which are not true synonymies. So for example, we saw that one-pad hypernymy kind of correlates well with true similarity. So we might also want to include one-pad hypernyms in the specialization thing, and you might even like expand your list of synonyms and antonyms like Ono et al. Did in their paper. And basically by doing all these like manipulations of linguistic constraints, you can boost your model to become better and better. So for example, we did that, and some of the evaluations on the like Simlex and Simwork that capture true similarity show that we can even like do better, like, or on a par with human interannotator correlation scores on these data sets, which even invalidates the data sets a bit. Okay, so another another application where we really see that the linguistic constraints can steer the specialization process is this work from Gertz et al., where like Attractor Pell or paragram style model was actually included as part of language model training, where you are trying to learn better parameters of rare words which are morphologically or in subword terms similar to words for which you have better estimates. So you kind of do this specialization after every cycle of language modeling pre-training, and you learn better language models along the way and get perplexity improvements. So that's a really rough explanation. Then what Lengerich et al. Did was kind of generalizing the retrofitting model to other relations, so not only to similarity, so that you can actually kind of model an arbitrary relation. So that's an interesting paper, but I don't think we have enough time to go through all the details. So, but just remember, okay, this could be seen as sort of like a retrofitting generalization to more relationships. Okay. Concerning linguistic constraints, it's basically, as I said, we can actually get linguistic constraints from different resources here and even at the same time. And we can also use cross-lingual constraints. So we'll see more about that in the cross-lingual section later on. And we did some analysis and basically showed that all sorts of constraints are useful. So like monolingual synonyms, monolingual antonyms, cross-lingual synonyms, antonyms, they all contribute to the overall performance of the specialization model. Then another interesting thing is, yeah, maybe everything is kind of, captured in the lexical resource. So does it matter if we start from random vectors instead of distributional vectors? And it seems that it's still, distribution information is still useful, and we get better scores when we start from non-randomly initialized distributional spaces compared to randomly initialized ones. And so this is again the overview slide that I already showed. So the main problem with post-processing methods is that they only affect words that are in the external resource. So basically what we want is full vocabulary specialization. Can we kind of propagate this external signal into the entire space? And then there are like several solutions there. So the first one is called explicit retrofitting, where the idea is not to kind of fine-tune the vectors based on these linguistic constraints that you have, but use the linguistic constraints as training examples of your models. So you basically want to, given this large list of linguistic constraints, you want to learn like a global mapping function that will perturb your vector space to emphasize the similarity relationship. And the way we implemented this was basically like a deep nonlinear feed-forward network with several layers. And why you need nonlinearity if you do the mapping, it's basically because you need to capture like millions of relationships between different words in the space. And the training proceeds pretty much exactly in the same way as fine-tuning for Attractor Pell, more or less. The only idea is that we want to do this like explicit mapping now, and not the fine-tuning, thing. So, and regularization is also pretty much the same. So I don't have time to now dig into the model, but it's important to understand that the main concepts. And then what was done was basically some even like diagnostic experiments where, for example, with Simlex, we encountered that most of the Simlex words were actually covered in lexical resources. So if you just do a Attractor Pell specialization model, you will get really good results. But what happens when you remove all these constraints containing these words from the training, what happens with Attractor Pell is actually performance stays exactly the same, which kind of proves, the model affects only words that are in the external resource, while at the same time, this explicit retrofitting model can actually learn a mapping function that will improve on the true similarity scores on Simlex. And we also saw the same thing on downstream tasks where, the explicit model, retrofitting model was like on a par or even better than the Attractor Pell model. And remember that it also, one important factor is also the amount of seen words in the lexical resource. Okay, then another similar model Another model that tries to do full vocabulary specialization is the post-specialization model, which can be seen as a two-step process where you first fine-tune your word vectors using Attractor, Pell, or retrofitting, or some other model, and then you know like how the vectors of these seen words looked before the procedure and how they look now after the procedure, and what you're trying to learn is then the mapping function based on the perturbations of the seen words and applied on the entire word vector space. And that's like first step, Attractor, Pell, second step, learn the mapping, then third step, apply to the full vocabulary, and you get the full vocabulary specialization. Again, it can be implemented as a deep feed-forward network, and you can actually we tried like different objective functions like standard squared errors minimization or the max margin framework like before, and it turns out that the max margin variant actually works better. Linear models work worse than nonlinear models, which is different than cross-lingual word embeddings research, but only like linear maps seem to work for us. But the intuition here is that it's again because Attractor Pell does like millions of small fine-tuning operations on the vector space, and these like differences cannot be captured by a simple linear map. While with cross-lingual word embedding learning, you just have like a linear map learned on top of 5,000 translation pairs, for example. And yeah, so the results show boosts on these similarity benchmarks. Also, when you have like zero lexical or holdout setup, is zero lexical overlap between evaluation words and words that are seen in the resources. Okay, and then another improvement of the basic model is now based on adversarial training, which is, yeah, you probably know how adversarial learning works. Which instead of just learning like a deep nonlinear feed-forward network, what we are trying to do here is also to discriminate between words that are in like true specialized target space. It's the same language, but it's true specialized target space, and words that you generate by learning the post-specialization function. So that's the main idea, and so your generator is trying to deceive your discriminator by generating better and better examples of perturbed word vectors specialized by your mapping function, while your discriminator is trying to capture whether they come from the originally Attractor Pell specialized space or the ones that you actually created by applying the mapping on the vectors. So that's the main idea, illustrated with this figure here. Formulated by these three sets of equations here, and so I already said this. This is just for completeness on the slides, and the idea is again to tie these three losses together. So like the discriminator generator and the max margin loss, or you can again do like mean squared error if you want, or any other loss as before. And it seems to work better than the original deep feed-forward network specialization, and it improves also like downstream tasks of lexical simplification, dialogue state tracking. So the results back then, so some of the results on dialogue state tracking were with the model that was state-of-the-art back in the day. Now we have more powerful models, so the numbers actually with all vectors go up, but that's irrelevant for this type of analysis. So basically, to recap the whole thing, the idea behind post-specialization, it's okay, you have your source language vectors, you do Attractor Pell or any other retrofitting model on the subset space of seen words, and you perturb that subspace, then you learn the mapping function from based on word vectors from that subspace, and you can apply it globally to the entire subspace. And a good thing, so it's kind of like an intro towards cross-lingual specialization here, is basically that if you have a shared cross-lingual word vector space, if you learn your mapping function on your source language space, you can even readily apply it on your target language space if you assume like a perfect shared cross-lingual space. But we'll see more about that in the cross-lingual part of the tutorial, and I think my time is up, so I'm giving the floor to Goran.
Hi, thanks to Ivan for this exhaustive part on the specializations for similarity. In this second part, we're going to focus on specializations of distributional spaces for asymmetric relations, primarily when we say asymmetric relations, we mean in 99% of the cases, and most of the work is about hypernymy or lexical entailment. And arguably that's a very important relation because it's a backbone of all the hierarchies that you want to build from your data. And other than hypernymy or lexical entailment, maybe we care about meronymy occasionally, part-of relation, which is also an asymmetric relation, but there are fewer applications for detecting meronymy. The difference in detecting or specializing for asymmetric relations compared to specializing for symmetric relations that Ivan covered, similarity is a symmetric relation, right? And is that we don't need to only capture the notion of similarity, but we also need to capture the notion of hierarchy. So car is somehow similar to vehicle, but there is they're of different level of generality. So vehicle is more general than the car, and we need to capture this notion of hierarchy as well when we specialize. So what matters if we're talking about Euclidean spaces is both the direction of the vectors while we're specializing them, but also the size, the norms of these vectors. We're going to go through same families of models as Ivan did in the symmetric specialization case, but we're going to emphasize the asymmetric aspects and how we capture this asymmetry in the objectives. Before we dig into these main paradigms, like joint specialization models for lexical entailment, retrofitting, post-specialization, and explicit retrofitting, we're going to do a quick detour into two topics that are not really specialization per se, but closely related. So just for completeness, we show a bit about that too. The first is about detection of asymmetric relations. So you can have a task where you just want to predict, given two distributional vectors, you want to predict whether the asymmetric lexical entailment hyponymy hypernymy relation holds between them. Meanwhile, you don't need to. Your aim doesn't have to be to specialize or to tune to change the vectors. You just feed the vectors as input and predict some output. So that's kind of a different task. You're detecting whether the relation holds, but it's closely related. So what people have done is try to do it in an unsupervised way, relying on some meaningful hypotheses like distributional inclusion hypothesis or distributional informativeness, but also in a supervised way, you feed what we would use as constraints in specialization, pairs of words that actually stand in that relation. You would treat it as training examples for a supervised model that doesn't tune the vectors, but predicts whether a relation holds. Distributional generality hypothesis as an unsupervised method or a measure of lexical entailment simply says that, kind of codifies that if you have a hypernym and a hyponym, then hyponym terms being more general, they will appear in more different contexts than the more specific terms. So the hypernym context will kind of inherit all the hyponym context, so they will have a larger entropy than the hyponym. So other than similarity, you can compare the entropies of the vectors and figure out which one is the hyponym. Distributional inclusion hypothesis is somewhat related. It says that if you have a hyponym V and a hypernym W, then your hyponym is expected to appear in all the context in which your hypernym can appear, but not vice versa. So I can't put my hyponym into all the contexts where I have my hypernym. And basically we quantify that. For a detailed overview of unsupervised LE detection measures, you can take a look at this paper from EACL 2 years ago. In terms of supervised models for predicting lexical entailment, there's the Hyperbolic model where they actually, for every pair of words that they need to predict whether the relation holds, they go into a corpus, they look at all the dependency paths in the settings where these two words co-occur, and they encode all of those different sentences or dependency paths in which they see both words with an LSTM encoder, and then the encoding of all the contexts in which the two words co-occurred is fed into a classifier which predicts the relation, and they train it on a larger training set. Something similar is our model from 2 years ago. where we don't go into the corpus, but we also feed the distributional vectors, transform them in several different ways. We'll learn different slices of tensors, and it's asymmetric because if the word appears in the left side of the pair, it goes through one set of projection matrices. If it's on the right side of the pair, it goes to another. So one tensor is kind of specializing to emphasize the properties of hypernyms, the other of hypernyms. And in the end, you have a bilinear product of the transformed representations and to make a predictions. This is already a step towards the specialization models, because these vectors here that go into the bilinear product can be seen as different specializations of these input vectors that are suitable for predicting the lexical entailment. But we don't really capture them. We only cared about the final prediction. So it's strictly speaking, it's not a specialization model. Another quick detour that we have to make when we talk about lexical entailment hierarchies are hyperbolic embeddings, where the idea is, the motivation for hyperbolic embeddings is that the Euclidean space is not really optimal for modeling hierarchies, and effectively all our distributional models, Virtuvac, GloVe, FastXL, we all get, from all of them, we get the vectors in a Euclidean space. So maybe we want to start from some kind of a graph of concepts that we extract. Either it's given to us as a hierarchy in WordNet, or we build some kind of a coherence graph from a corpus, but we have a structure, a graph from which we can then induce a hyperbolic embedding space. It's a non-Euclidean geometry, and it accounts for spaces where you have constant negative curvature. And there were several different models proposed more recently. The first one that drew attention was the Poincare ball model from Nickel and Killa in 17, where you assume this is just a depiction of a two-dimensional Poincare ball. That means that the embeddings have only two dimensions, basically. And you wanna learn these embeddings U and V for pairs of words, and in your hyperbolic space in a Poincare ball, this is the difference. This hyperbolic arcus cosinus is your distance between these two hyperbolic embeddings. And depending on what your downstream task is, you want to use you want to learn your d-dimensional embeddings on a hyperbolic on a d-dimensional ball, where you're trying to minimize the set of constraints. And if you feed, for example, WordNet, then you have pairs of words that are in hypernym relation, and those words you want to minimize this loss function that is based on these hyperbolic distances between those words that you know that the relation between them holds in a resource. Strictly speaking, this is also not a specialization model, because you don't start from some kind of vectors for the words, but you rather start from a symbolic hierarchy and then induce the vectors from scratch, not in a Euclidean space, but in a hyperbolic space. Yeah, I have the same problem now. The presentation stopped working. Apparently we have a timer of some kind. Okay. Yeah, so after this brief detours into things that are related but not strictly specialization, let's go into actual specialization models for lexical entailment. Again, we will look at the joint specialization models, and then these three families of models for post-processing, classic retrofitting, and then post-specialization and direct specialization as models that can specialize the entire distributional space for your relation of interest. This is the same slide that Ivan had. Basically, you can have the same difference between the models. You have joint models, which are somehow injecting your asymmetric lexical entailment constraints into the learning objectives of the embedding models, whereas the post-processing approaches take the pre-built distributional space, your embeddings, and then tune something on them. The difference is now that we somehow need to add, all of these models need to account for asymmetry and to acknowledge that this is now an asymmetric relation, not a symmetric one anymore. The first model that I would mention, again, strictly speaking, is not really a specialization model, because there's no classic distributional coherence objective. There is just the objective based on the constraints. The constraints are hypernymy constraints, but also co-hypernymy or co-hyponymy, two words that have a common hyponym or two words that have a common hypernym. And for each pair of words, you have also this third number, Q, which is the number of times the frequency you've seen it in a corpus. And you're learning two different embeddings for each of the words. One is to represent it as a hypernym, this O embedding, O function, and the other is to represent as a hypernym, the E function. And you're trying to minimize, if I have a pair of words, I map one to be a hypernym, the other one to be a hypernym. I want to minimize the distance, and in that sense, I'm enforcing my asymmetric relation. The training is based on max margin objective here, as quite often. This F is basically just a comparison of the two vectors after they've been projected. And X is a real example, X prime is fake negative X corresponding negative example where you pair one of the words with some other word which is not in the lexical entailment relation of the first one. And then you're trying to make the score of the true couple be bigger than the one of the fake couple by some margin. But what's interesting here is that the margin is not a fixed one, as in many models, but it's a dynamic one and depends on this Q, which is the number of times you've actually seen this pair in the corpus. So the stronger evidence you have from the corpus for a particular constraint, the bigger the margin of that positive example with respect to corresponding negative example is. Next in line is a true specialization model, joint specialization model for lexical entailment, which is from Tuan, from EMLP 16, and that's effectively a CBOW model that's been modified. Its context definition has been modified so that your center word is kind of the hypernym, and you add to the context the hyponym of the pair. So if I have a context in which my hypernym is appearing, I add from my lexical resource set of its hyponyms, and then I encode that context and I want to predict my hypernym word. So it's basically, there's no modification to the model. So it's basically CBOW, but there's a context manipulation that is based on the constraints that come from external resource. These two models have actually been shown that they don't really capture, they can predict whether, for a pair of words, whether they stand in a lexical entailment relations once you specialize the vectors, but the norms haven't been really changed in such a way that you can predict directionality. So you can't say which word is a hyponym and which is a hypernym in a pair. So they lack explicit asymmetric terms in their objectives. So the joint specialization model that actually introduced it kind of more explicitly is the Hypervac model that looks into two different types of contexts in which you find the lexical entailment pairs. So if I find my context in which I have my hyponym bird and a hyponym animal in the context of the word wing, which is a property of the bird, not the animal, so it's a property of the hyponym. And I have a similarity with the hyponym, which is bigger than the similarity with the hyponym by more than some threshold. So wing is going to be more similar to bird than to animal by some margin. In that case, I know that I have a context in which my hyponym should go closer to the hypernym. So bird is an animal, and I'm going to push the bird towards the animal, but not the other way around, because this is a context in which I have wing, and if I pushed animal towards the bird, that would mean emphasizing that animals have wings, and not all animals have wings, sure. The other way around, if you have a difference which is smaller than a threshold, that means that you're in a context where you have some word which is kind of similar with both the hyponym and the hyponym. So if you have the word rights, animal rights kind of applies to bird rights as well. So it's similar, the rights is as similar to animals as maybe to birds, or even more to animals than to birds. So in that setting, I want to push my my bird closer to the animal, because I want to give bird this property, because animal rights are bird rights as well. So I want to push my bird closer to the animal. And then I augment my skipgram negative sampling objective, which is a standard word embedding objective. I augmented with these two additional objectives that, depending on the type of context, move either the hyponym closer to the hypernym or the other way around. Again, this is the slide that I repeat, but it's worth repeating. Joint models are kind of heavyweight because you need to find a way to augment your objective of your embedding model with the constraints that you have. And that means that if you want to specialize different embedding models for the same lexical relation, you would need to design different specialization models. And then you need to retrain everything on the entire corpus and so on. So the idea would be, can we apply some kind of lexical asymmetric, lexical entailment specialization in the same retrofitting type of style as a post-processing step once we've actually built the distributional vectors? And yes, we're back to retrofitting and co. There is a lexical entailment variant of the Attractor Pell model that Ivan and colleagues published last year. And the idea is basically just to augment the attract and repel terms that you have for synonyms and antonyms with additional constraints, objective constraints that come from the LE constraints, lexical entailment constraints. So what you basically add is additional attract objective for all the hyponym pairs and the asymmetric norm-based objective that tells you, the hyponyms should have a smaller norm than the hypernyms. So this is how this additional asymmetric objective looks like to the left. So in the denominator we have a difference of the norms, so that's why it captures actually the asymmetrically the fact that hyponyms should have smaller norms than the hypernyms. And the final objective is no longer just attract for the synonyms, is no longer just attract for the synonyms and repel for the antonyms and the regularization, but we have attract for the lexical entailment terms. So hyponym pairs should also be more aligned in the directionality. So car and vehicle are kind of similar as well. But we also want to enforce this objective that tells us that the norm of car should be smaller than the norm of the vehicle. And then we're back to the same problem of the retrofitting models, is that okay, now we're specializing the words from the constraints for lexical entailment, but we're not going to change any vector that doesn't belong to a word that we haven't seen in the constraints. And ideally, we'd like to specialize for lexical entailment the entire distributional space. And again, we can resort to two different approaches for doing that. One is avoid retrofitting altogether. This is the option 2. So we do direct or explicit retrofitting for entailment. Or the first option is post-specialization, where we say, okay, we have retrofitting, so for the seen words we know the initial vector and the final vector. Now we can make the mapping explicit by learning from these examples of seen words. So this is the work from Repel for NLP workshop this year, representation learning. The idea is the same, so you're as in the similarity-based post-specialization, you're retrofitting. Your Lear model gives you the specialization of the vectors that you only a small subset of your distributional space that corresponds to the words you've seen in your constraints, but those are enough to serve as training examples. So these white boxes are your distributional vectors of seen words. The corresponding purple boxes are what you obtain with Lear after the specialization, and then treating those as input-output pairs, you can make the specialization function explicit and then apply it to the rest of your distributional space. And again, you can make the post-specialization adversarial in a sense that instead of just learning the mapping between the distributional and retrofitted vectors, you can add a discriminator that is trying to guess whether a vector came by being mapped, being projected, or it was a true retrofitted vector that came directly from Lear. And if you have a generator that, other than minimizing the distance after projection, also tries to confuse the discriminator, you get the better results. Okay, this is just the losses of the adversarial model. In the direct or explicit retrofitting for lexical entailment, it's again the idea that we don't want to do retrofitting at all. The idea is we can skip the retrofitting and use the constraints directly as training examples for tuning, for learning the explicit specialization function. So the idea is that I feed in my distributional space, I feed in my distributional space, I feed in my constraints, synonymy, antonymy, lexical entailment constraints, and I get an explicit function. If I capture that explicit function, then I can specialize the entire distributional space with that explicit function. Whereas the retrofitting does this, basically just specializes the vectors of words that you've seen, but not the rest of it. So the specialization function is again a simple feed-forward network, and but it's trained directly with the constraints, unlike in post-specialization where we trained on raw distributional and retrofitted vectors. Here we just feed the raw distributional vectors and we define the losses that say these words after specialization, they need to be in this relation. We kind of predict the relation. The important component, again, compared to the specialization for similarity, is that you need to have an asymmetric loss. So if you notice here, this is very similar to Lear, but in Lear you were directly updating here the distributional vectors, whereas here you're not updating the distributional vector, but you're asking something to be satisfied, a certain max margin based objective, but after the projection. This F means feeding this input vector into a feed-forward network, and we want to tune the parameters of this network, so that's the difference. And again, we have this the same asymmetric loss there. And then for different kind of constraints, we have different combination of loss functions. So for lexical entailment, we have attract kind of constraints and these asymmetric constraints. For synonyms, we just have the attract constraints, and for antonyms, we have kind of repel or push apart constraints. Yeah. Okay, these were again just a repetition of the main retrofitting paradigms and then post-specialization and explicit specialization paradigms, but for the asymmetric relation of lexical entailment. The question is now, how do we evaluate and what are the resources, and how do we see actually how well we tune these vectors for this asymmetric relation? Typically you have 3 different tasks in which you're trying to see whether you can predict well from your vectors. The first is the detection, so just given 2 words you need to predict whether they hold in lexical entailment relations versus other relations that you have in your data set, like synonymy, antonymy, co-hyponymy, meronymy, and so on. The directionality task is about saying, okay, I give you the pair of words, you predicted that they are in the lexical entailment relation, but now you need to predict the direction as well, which one of them is hyponym and which one is hypernym. And finally, the graded lexical entailment is an evaluation where you assume that lexical entailment is not a binary relation, but there is a grading to it. So you want to predict a score that denotes a degree to which the first word is a type of the second word. Okay, so here are some evaluation data sets for the lexical entailment detection, and they're typically reasonably small. So they were mostly used in this older type of models where you had unsupervised lexical entailment detection scoring functions, like based on distributional inclusion hypothesis and so on. The BLESS dataset, the evaluation dataset, Weeds and Benotto, they are always lexical entailment pairs versus pairs that stand in other relations, and these other relations are the usual candidates like synonymy, antonymy, or meronymy, coordination, and stuff like that. You have some variants that are then specialized, focusing on directionality, not just detection, like BBLESS, and so on. But in those detection models that I mentioned before, HypeNet or the dual tensor model, these were neural models for which you needed actually more examples of hypernymy and other relations to train as positive and negative instances. And for that purpose, the bigger data sets were created from WordNet or other external databases containing tens of thousands of training examples, and those can be used as well for evaluation. Finally, the graded lexical entailment, which is arguably the most important or most relevant type of evaluation for the specialization, because you want to actually measure how well you tuned the vectors for hypernymy. So you want an actual score, how far they are in the hierarchy, not just whether they are one more general and one more specific. So this is the task of graded lexical entailment. So if I give you the pair of words, you need to predict the degree to which the first word is a hyponym of the other word. Arguably, I mean, this has some backup in the psycholinguistics and some theories behind. Arguably, if I ask you, is cinnamon a food, you might say yes, but if I ask you, is bread more of a food than cinnamon, you will also say yes, so there is some kind of grading to it. That's the idea. So the main resource on which we perform graded lexical entailment evaluation is Hyperlex. It consists of 2,600 something pairs of words that are on a 0 to 6 scale, annotated by 5 or more annotators. And you have pairs in different relations, and it's de facto standard for evaluating lexical entailment. And from human scores, you can actually see here, more recently we have done variants, and I'll talk about that later in the cross-lingual part. We've done variants of Hyperlex in other languages as well. But you can see from the distribution in English especially that while you have most of the scores are on the edges, like 0, 1, 5, 6, you have decent amount of pairs where people graded something in between, like a score of 3 or 4. So it is a graded relation. And this is just to show that graded lexical entailment is quite different from semantic similarity. So there is this hierarchy or dimensionality component, and the correlation is pretty low with the semantic similarity scores. So if we evaluate LEAR, which is, remember, a retrofitting model for lexical entailment, here we see that it outperforms actually these previous models like Hypervac, which is a joint model, and also outperforms significantly the hyperbolic embeddings in predicting the relations. There is one caveat though, but it's not an unfair advantage compared to hyperbolic embeddings. They use the same, and also the Hypervac kind of. But LEAR specializes only the words, only the vectors of words that have been seen in lexical resources and in lexical constraints. And in Hyperlex, 99% of the words in Hyperlex have been seen, exist in the constraints that the retrofitting model LEAR tunes. So this is a favorable setting for the retrofitting models, and in some kind of downstream task where you want LE specialized embeddings, you cannot expect that all of your words that you will see in your downstream task, that you have also seen them in your lexical constraints, so you tune the vectors for it. So the general lexical entailment model, so the explicit direct specialization model, this is a comparison in the different setups where we actually remove from the constraints some percentage of words from Hyperlex, from the final evaluation setup. Not pairs, we don't have the same pairs, but words. So you can see that if we remove all the constraints that have any of the Hyperlex words in it from the constraints, then LEAR cannot do anything on the rest of it because it tunes only the words from the constraints. Since none of the Hyperlex words in the 0% setup is in the constraints, nothing happens, and this is the actual score of the distributional space. GLEN, or generalized tuning, can learn still the good specialization function from the other constraints that don't contain any Hyperlex words, and generalize as well to the Hyperlex setup. So this is the difference between explicit or post-specialization, which can generalize and fine-tune the whole space, versus the standard retrofitting, which only changes the vectors of words. But as you move towards the, retrofitting model has seen all the constraints, then it gets very good because it can really fine-tune, whereas the explicit specialization model has to smooth over all of the constraints in order to be able to generalize for the other words. This is just a comparison of LEAR and post-specialization, maybe even more meaningful or more directly comparable, because post-specialization is making the specialization function explicit from the examples that the retrofitting model fine-tuned. And you can see that, again, in the settings where you expose your retrofitting model to a smaller number of your evaluation words, it hasn't seen them in the constraints, it can't do much, whereas the post-specialization can still generalize well from the other constraints and specialize the Hyperlex words as well then. Okay, I think it would make sense. Now is 3:30, so it's a good point to make a break before we continue with the other section.